In the heart of the galaxy, NGC 3227, a supermassive black hole sits buried behind tangled lanes of dust and gas. Yet something is disturbing this cosmic fog interactions with a neighbouring galaxy, and the restless activity of the black hole itself stirring the clouds into chaos. Today we explore what is really happening inside this turbulent core. If you enjoy journeys into active galaxies like this, please like, subscribe and share, and tell us in the comments, what would you ask about a black hole wrapped in such chaotic dust and gas? Thank you for watching. Now let's begin. On the sky of Earth, a small faint smudge in the constellation, Leo marks a spiral galaxy whose light has travelled for tens of millions of years before reaching modern telescopes. This system catalogued as NGC 3227 belongs to the same broad cosmic neighbourhood as the Milky Way, yet lies far beyond the local group that contains the Milky Way and the Andromeda Galaxy. From Earth it looks modest, but in space it is a full-sized galaxy with a vast disk of stars, gas and dust seen at a distance, where its overall structure can still be examined in some detail. The light that now enters detectors left the galaxy when life on Earth was already complex, but the present arrangement of continents and ecosystems had not yet formed, so each observation is also a look back in time. Astronomers estimate the distance using several methods, including the apparent brightness of characteristic stellar populations and the general scaling between galaxy size and luminosity. And while individual values differ all place, this object many tens of millions of light-years away. In surveys that map galaxies over hundreds of millions of light-years, it appears as one point among many, yet its properties make it a useful example of how a galaxy can interact with its surroundings and host an active centre at the same time. The first recorded observations described a faint nebula near another fuzzy patch, long before it was understood that such nebulae are entire galaxies outside the Milky Way. The neighbouring patch is now known as NGC 3226, a dwarf elliptical companion. Modern imaging reveals that the pair is physically associated, not simply aligned by chance. Long tidal streams and diffuse plumes of stars and gas stretch between them and curve around their outer regions. These features trace the slow action of gravity over hundreds of millions of years, as each galaxy pulls on the other and draws material out of their outskirts. Together they form the core of a small galaxy group named after the brighter spiral member. This group sits in the wider Leo region, on the outskirts of the Virgo supercluster, one of many knots in the network of filaments and clusters that make up the large-scale structure of the universe. In this environment, galaxies are neither packed as tightly as in the core of a rich cluster, nor as isolated as those in deep cosmic voids. Instead, they move through a moderately dense setting, where repeated encounters and steady infall of intergalactic gas are both possible. Radio observations of neutral hydrogen reveal extended clouds that reach well beyond the visible disks. Faint bridges of gas link the spiral galaxy and its dwarf companion, while additional streams trail away into intergalactic space. These structures show that the group is still dynamically active, and that the history of the main spiral includes episodes of stripping and accretion. Ultraviolet and infrared observations add further information. Ultraviolet light highlights regions of recent star formation in parts of the disk, while infrared data reveal warm dust grains that re-radiate absorbed starlight and energy from the central regions. Together, these wavelengths confirm that the galaxy is still forming stars, and that dust plays a significant role in shaping how its light emerges. Spectroscopic observations which separate light into its component wavelengths show both the smooth continuum from stars and sharper emission lines produced by gas excited by energetic radiation. The overall spectrum indicates that the nucleus of the galaxy is unusually bright compared to its stellar background. This is one reason it is classified as a Seyfert galaxy, a type of active galaxy, where the central region produces extra light across a wide range of wavelengths. Seyfert systems are common in the nearby universe and are thought to represent phases where central black holes accrete at moderate rates, rather than in the extreme regime associated with luminous quasars. Because they are close enough to resolve with modern telescopes, they serve as detailed laboratories for studying how energy from a compact nucleus interacts with the host galaxy. In this spiral, signs of nuclear activity appear in optical ultraviolet infrared and X-ray observations, each probing different components of the central engine and its immediate environment. From the large-scale perspective, the galaxy can therefore be seen as a node where several influences meet. The tidal pull of the dwarf elliptical companion distorts its outer regions and helps remove angular momentum from gas in the disk. The gravitational field of the wider group affects the orbits of both galaxies and shapes the long streams of hydrogen seen at radio wavelengths. The surrounding intergalactic medium provides a reservoir of additional gas that can slowly fall in along filaments over billions of years. All of these processes supply and rearrange the material that ultimately can move toward the central regions. At this outermost level of description, the focus remains on placement and setting rather than on the details of internal structure. The spiral galaxy is part of the Leo 2 groups, which in turn lie within the Virgo supercluster, and its location can be plotted in three-dimensional maps of the nearby universe, where filaments, walls, clusters and voids form a web-like pattern. In that pattern, this system occupies a modest knot where a few dozen galaxies share a common gravitational environment. Its active nucleus and obvious interaction with a close companion make it stand out among other members, and these qualities make it a valuable target for observations designed to link large-scale environment-galaxy interaction and nuclear activity. Large optical and radio surveys revisit this field regularly, refining estimates of distance and group membership, and building time series that track slow changes in the nuclear light within the broader galactic setting. Around the spiral galaxy and Leo, other systems move in the same gravitational neighborhood, forming a small group bound together over billions of years, rather than drifting alone through empty space. The most striking companion is the dwarf elliptical galaxy known as NGC 322-26, which lies close in projection and also shares a similar distance, confirming that the pair is physically associated rather than aligned by chance. Deep optical and radio imaging show that the two galaxies are connected by long, faint structures made of stars and gas that arc away from the disks and curve into space as tidal tails. These tails arise because each galaxy exerts differential gravity across the body of the other, gently pulling material from the outskirts and stretching it into elongated streams as the pair orbits their common center of mass. The combined system appears in catalogues of unusual or interacting galaxies under the name ARP94, highlighting its disturbed morphology, overlapping halos, asymmetric outer isophotes and filaments that do not follow the smooth curves expected for an undisturbed disk. In radio maps of neutral hydrogen, the gas distribution extends far beyond the bright optical disks. A large envelope of hydrogen surrounds the pair, with bridges that connect the spiral and the dwarf elliptical and additional clouds that follow the arcs of the tidal features. Within this envelope, observers have identified a distinct cloud rich in gas that shares the general motion of the group but shows a velocity offset relative to the main disk of the spiral, indicating that it is a kinematically separate object, rather than a simple outer patch of the disk seen in projection. Optical and ultraviolet images reveal that this gas cloud hosts clusters of young blue stars embedded in a softer halo of ultraviolet light, marking regions of ongoing star formation in material that has been drawn out of the parent galaxy. The distribution of star-forming knots is not uniform. Activity is concentrated where the gas has relatively narrow velocity widths and lower internal turbulence, suggesting that calm pockets within the tidal debris are more likely to collapse and form stars than more agitated regions with broader line profiles, because the gas appears enriched in heavy elements and dust with properties more typical of material processed in a large galaxy than of a long isolated dwarf. Many studies interpret this object as a tidal dwarf candidate formed from recycled debris rather than as a long-lived independent galaxy captured from outside the group. This possibility illustrates one way in which interactions between galaxies can not only strip material, but also assemble new structures from the ejected gas. The overall group environment supports such processes. The spiral is the brightest and most massive member, while the dwarf elliptical and the gas-rich cloud occupy orbits within its extended halo. As the galaxies move, their mutual tides draw out streams, compress gas in some locations and thin it in others. Over cosmological time, such interactions can gradually reshape the stellar and gaseous components, thickening the outer disk, populating faint stellar halos, with material flung outward and seeding the space between galaxies with clouds that may later fall back. In this group, the dwarf elliptical shows signs that it may once have acquired gas from its spiral neighbour, although millimetre observations detect little molecular gas, at present implying that any cross-fueling is limited or transient. The gaseous bridges and tails trace the orbital history of the pair. By mapping the velocities of hydrogen along these features, astronomers infer that the galaxies have likely undergone at least one close passage during which the spiral disk was strongly perturbed and outer gas was drawn into arcs that now curve around the system. The presence of a dense gas cloud near the base of one tail, with stars forming in a compact region, suggests that some debris is beginning to condense into a bound structure, while other parts of the tail remain diffuse. Infrared observations from space-based telescopes add another layer to this picture. Warm dust glows along parts of the tails and bridges, especially where young stars have recently formed, while mid-infrared emission traces complex molecules and small grains that survive in the low-density tidal environment. These signatures confirm that the tidal features carry not only cold gas, but also processed material expelled from the inner disk regions during earlier phases of interaction. The gravitational field of the wider group also plays a role. Beyond the immediate pair, other fainter galaxies occupy the same general volume of space, forming a loose association known as the NGC 3227 group itself, part of the Leo 2 groups that extend outward from the Virgo supercluster. The combined gravity of this association helps keep the interacting pair bound, and shapes the larger scale orbits that bring them repeatedly close enough for tides to operate. Within such a setting, gas stripped from one pass does not necessarily escape forever. Some of it may reach large distances and then slowly rain back toward the central galaxy's long extended paths. In the case of the spiral and its dwarf companion, the distribution of hydrogen and the positions of the streams imply a complex pattern of removal and possible return with debris loops that may have dynamical ages of hundreds of millions of years. The same interactions that give rise to tails and bridges also subtly alter the internal motions in the outer disk. Stellar orbits become less regular near the regions where the tidal forces have been strongest, and gas flows may be deflected from simple circular paths into elongated loops that carry material inward on one side of the disk and outward on the other. Although detailed modelling is needed to quantify these flows, the presence of pronounced asymmetries and disturbed outer isophotes shows that the galaxy is still adjusting to the gravitational encounters that have drawn out its extended structures. This region of space therefore contains a mix of components at different stages of response to tides: stellar streams fading into the background, sky, gaseous arcs traced by hydrogen emission, compact knots of star formation in recycled debris, and companions whose paths are slowly reshaped by the group potential. The spiral galaxy and the dwarf elliptical do not evolve in isolation, but share mass angular momentum and energy with these surrounding features as they continue their slow mutual orbit within the wider Leo environment. On larger scales than the tidal tails and bridges, the main body of NGC 3227 appears as a barred spiral galaxy, whose bright disk central bar and winding arms form a connected stellar structure. Seen from Earth, the disk is moderately inclined, so neither fully face-on nor edge-on, and this angle allows astronomers to separate many of its components without losing them behind a thick layer of foreground dust. The luminous disk extends over tens of thousands of light-years, with most of the starlight coming from a flattened distribution of old and intermediate age stars that orbit the centre on nearly circular paths. Superimposed on this background is a more concentrated central bulge, a rounded light distribution near the middle that rises above the general plane of the disk. In this galaxy, the bulge is not as dominant as in some massive spirals, so the overall appearance remains disk-like, with the eye drawn not only to the centre but also along the line of the stellar bar. The bar is an elongated feature of stars and gas that stretches across the inner disk, aligned at an angle to the major axis of the galaxy. In near-infrared images which trace older and cooler stars with less disturbance from dust absorption, the bar stands out clearly as a smooth, bright structure several thousand parsecs in length. A parsec is a unit of distance slightly more than 3 light-years, so a bar of several thousand parsecs spans a large fraction of the inner disk. The stars in the bar follow orbits that are not circular but elongated, aligned broadly with the bar itself, and these orbits support the bar as a long-lived pattern in the gravitational field of the disk and bulge. Gas in the same region responds to this non-circular potential in a different way. Instead of simply following the stellar orbits, interstellar clouds feel pressure forces and shocks as they move along the bar, and they tend to pile up along narrow dust lanes on the leading edges of the bar relative to the direction of rotation. In optical images, these dust lanes appear as dark streaks that cut across the bar, partially obscuring the starlight behind them. Regions where gas slows and compresses along these lanes can become sites of star formation, so small knots of blue light often dot the bar near the dust features, although the rate and distribution of star formation along bars vary widely from galaxy to galaxy. Beyond the ends of the bar, the spiral pattern of the disk becomes more apparent. 2 main arms unwind from the bar ends curving around the galaxy, in a roughly symmetric way, though tidal interactions and internal instabilities add asymmetries and breaks. These arms are not rigid structures but regions where the density of stars and gas is enhanced compared with the surrounding disk. As material orbits through the disk, stars and gas move in and out of these patterns, spending more time in the higher density zones and thus making the arms stand out as coherent features over large distances. In the spiral arms, gas clouds compress under their own gravity and the external pressure of the surroundings, and this promotes the formation of clusters of young massive stars. These young stars shine brightly in ultraviolet and blue light, which makes the arms appear patchy and bright in those wavelengths, while the underlying older stellar disk glows more smoothly in red and near-infrared light. Dust mixed with the gas traces the shape of the arms as well. In visible images, narrow branching dust lanes outline the inner edges of the arms, following the curvature of the spiral. These lanes mark places where interstellar material has been compressed by the passage of a spiral density wave, a slowly rotating pattern in the gravitational potential of the disk. The galaxy's rotation curve, which describes how orbital speed changes with distance from the centre, is approximately flat beyond the inner few kiloparsecs, meaning that stars and gas in the outer disk move at nearly constant speed around the centre. This behaviour, common in many spiral galaxies, implies that there is more mass present than can be accounted for by the visible stars and gas alone, and so it provides evidence for an extended dark matter halo that surrounds the luminous disk. Within this overall potential, the bar and arms act as ways for angular momentum to be redistributed over time. The bar can transfer angular momentum outward, allowing some gas to drift inward, while other material is pushed to larger radii. The spiral arms can also exchange angular momentum with the disk stars and gas gradually altering their orbits. The extent to which these processes have reshaped the structure of this particular galaxy depends on factors such as bar strength, the rate at which the bar pattern itself rotates, and the history of interactions, but the presence of a clear bar and distinct spiral arms shows that features which break the simple circular symmetry of the disk play a significant role in its dynamics. The outer disk is not perfectly smooth. Warps and lopsidedness appear in both stellar light and gas distribution, especially where the outskirts overlap with tidal debris from encounters with a dwarf companion. In some directions, the disk seems to extend farther, while in others it is truncated or diffuse. Star formation in these outer regions tends to be sparse and patchy, taking place in isolated associations rather than in grand continuous arms. Observations at radio wavelengths indicate that neutral hydrogen extends beyond the optical disk, filling a thicker, more flared layer that gradually blends into the tidal features. Within the main disk, by contrast, the gas layer is thinner and more closely aligned with the stellar plane. The combination of a moderately inclined disk, a prominent bar, and winding spiral arms gives the galaxy its characteristic appearance in deep images. When viewed in different bands, the structural components emphasize different aspects of its history. Near-ultraviolet exposures highlight regions of recent star formation along the arms and parts of the bar. Optical broadband images show the balance between the smooth, older population in the disk and the clumpier, young population in star-forming regions. Near-infrared images trace the underlying mass in old stars and reveal the full length and shape of the bar and bulge with less interference from dust. Together, these views confirm that the global skeleton of the galaxy consists of a rotating disk anchored by a central concentration of mass threaded by a long bar and patterned by spiral arms that carry stars' gas and dust around the center on timescales of hundreds of millions of years. Beyond the bright stellar disk and its spiral arms, the galaxy carries an extended envelope of cold gas that reaches far into the surrounding space, forming a reservoir that is less obvious in visible light but clear in radio observations. Neutral hydrogen, traced by its characteristic emission at a wavelength of about 21 centimeters, outlines a structure that is broader and more irregular than the optical disk, with extensions that follow the directions of tidal bridges and tails, as well as regions that fan out into a more diffuse halo. In maps made with radio interferometers, the main disk appears as a concentrated region of emission, where the gas rotates in an orderly pattern around the center, while beyond that region, lower surface brightness features spread over a much larger area and show signs of disturbance. Some of these outer structures take the form of elongated plumes that curve away from the disk, blending into the tidal streams that connect the spiral galaxy to its dwarf elliptical companion. Others form arcs and patches that seem only loosely attached to the main body with line-of-sight velocities that differ from simple extrapolations of the inner rotation curve. The gas in these outer zones resides at relatively low densities compared with the dense clouds found in the inner disk, yet even such tenuous material contributes significantly to the total gas mass of the system. Because the atomic hydrogen is mostly cold, with temperatures of the order of a few hundred to a few thousand Kelvin, it does not shine brightly in optical wavelengths, and so the presence of this extended component became clear only with sensitive radio surveys. In some directions, the gas halo extends to radii several times larger than the optical disk, indicating that the gravitational influence of the galaxy reaches well beyond the limit suggested by starlight alone. The velocity field of this neutral hydrogen reveals both ordered rotation and irregular motions. Close to the disk, the gas orbits in the same general sense as the stars, with a nearly flat rotation speed that changes little with radius. Far farther out, deviations from simple rotation become more prominent. Portions of the halo show kinks, warps and twists in their velocity patterns, reflecting the combined effects of the galaxy's own gravitational potential, the pull of the companion and the inertia of gas that has been drawn into tidal structures. In some regions, the gas seems to be falling back toward the disk along curved paths, while in others it appears to be drifting outward along the tails, perhaps to be lost to intergalactic space, or to linger in extended loops for long periods. Small high-velocity clumps sometimes stand out against the smoother background field. These compact features may represent fragments that have been recently stripped, or condensations forming within a larger stream, and their motions give additional clues to how material is exchanged between the disk, the halo, and the wider group. Superimposed on this neutral component is a smaller fraction of ionized gas that can be traced in optical emission lines near the inner parts of the halo, especially where young stars or the central active region provide radiation capable of removing electrons from hydrogen atoms. However, the bulk of the outer reservoir remains neutral and relatively cool, shielded from strong radiation fields by distance and by self-shielding in denser clumps. The distribution of this material is not uniform in angle. Some sectors around the disk display thick, well-populated extensions, while others are comparatively empty, suggesting that the history of stripping and accretion has been anisotropic. This pattern likely reflects the specific orbits of the galaxies in the group and the directions from which gas has been drawn out during past encounters. The presence of a gas-rich cloud near one of the tidal tails with properties similar to those of the extended halo indicates that parts of the reservoir have condensed into more concentrated entities that may evolve as dwarf-like systems for some time. Elsewhere, the halo appears more filamentary or sheet-like, with long low column density stretches that bridge the gap between the main disk and the wider intergalactic medium. In the vertical direction away from the plane of the disk, the gas layer flares and thickens so that at large radii the halo resembles a broad, gently curved envelope rather than a thin sheet. Within this outer reservoir, small fluctuations in density, temperature and pressure create a complex, clumpy structure. Local overdensities can in principle cool further and begin to collapse, while underdense regions expand and become more diffuse. The timescales for these processes are long, often spanning hundreds of millions of years, so at any given moment the halo contains a mixture of gas that is slowly cooling, gas that is roughly stable, and gas that has recently been disturbed by tidal forces or by weak shocks. Interactions with the surrounding environment also shape the halo over time. As the group moves through the larger-scale cosmic web, it encounters variations in the density of the intergalactic medium, and these variations can compress or stretch the outer gas. Gentle ram pressure from diffuse intergalactic gas may remove some material from the farthest reaches of the halo, especially where it has been raised out of the gravitational potential by tidal forces, while other regions may accrete fresh gas from filaments that thread through the group. The chemical composition of the outer reservoir, including the presence of elements heavier than helium, shows that much of this material has been processed in earlier generations of stars rather than remaining pristine since the early universe. This enrichment links the halo to the long-term cycle of star formation, stellar evolution, and mass loss in the galaxy, and it means that even the faint outskirts carry the imprint of many past episodes of activity. The balance between removal and accretion determines whether the total mass of the reservoir declines or remains nearly constant over cosmological times. Embedded within this extended structure, the bright optical disk and bar occupy only the central part of the gravitational well, while the halo of cold gas forms a more spacious and slowly evolving component that surrounds and connects the visible galaxy to its larger scale environment. On scales smaller than the broad stellar disk and the extended neutral gas halo, the inner regions of the galaxy's disk are marked by a dense network of dust lanes and molecular clouds that thread through the bar and the bases of the spiral arms. In visible light, these lanes appear as narrow twisting bands that dim and redden the starlight behind them, but physically they represent concentrations of cold gas and dust mixed together in elongated structures that follow preferred paths in the gravitational potential. In this system, the most prominent dust lanes lie along the leading edges of the bar, with respect to the sense of rotation slightly offset from the brightest ridge of starlight. As gas orbits within the bar, it encounters these regions as zones of compression and shock, where its motion is redirected and its density increases. The result is a pair of strong, almost straight features that run inward from the bar ends toward the central parts of the disk, cutting across the otherwise smooth light distribution of the inner galaxy. Additional, more curved dust lanes extend from the bar into the inner spiral arms, tracing the transition between bar-driven flows and the larger scale streaming along the arms. Observations at millimeter wavelengths which detect rotational emission lines from molecules such as carbon monoxide show that the bulk of the galaxy's molecular gas resides within the inner few kiloparsecs. A large fraction of the total carbon monoxide emission comes from this zone, indicating that the cold, dense phase of the interstellar medium is strongly concentrated toward the center rather than spread evenly across the whole disk. Within this region, the molecular gas is not smoothly distributed. Instead, it forms a hierarchy of clumps and complexes whose sizes range from tens to hundreds of light years, embedded in a more diffuse background. The dust lanes coincide with many of these complexes, especially along the bar where orbit crowding and shocks gather gas into elongated ridges. Local peaks in column density within the ridges represent places where gravity overcomes internal turbulence and pressure support, allowing parts of the gas to begin collapsing. In some of these locations, the collapse has already progressed far enough for young massive stars to have formed, and their radiation ionizes the surrounding hydrogen, creating compact regions of ionized gas that shine strongly in specific spectral lines. Imaging in light from hydrogen recombination picks out strings of such regions along the leading edges of the bar and within the inner arms, confirming that the dust lanes are not only accumulators of gas, but also preferred sites of star formation. Infrared observations show that warm dust grains glow in many of the same places heated both by the general stellar radiation field and by nearby young stars. These data together indicate that the inner disk contains a complex multi-phase medium in which cold molecular clouds, warmer atomic gas and dust coexist within a few hundred parsecs of one another, structured by the underlying gravitational potential and by the internal physics of the gas. Kinematic measurements of the molecular lines reveal that the gas in the inner disk follows orbits that deviate significantly from simple circular motion. Along the bar, velocity shows strong streaming patterns, with components directed along the bar's length and toward the center. Near the dust lanes, abrupt changes in velocity correspond to shocks where gas crossing the bar potential loses part of its angular momentum and settles into new paths. In the inner spiral arms, the velocity field becomes more curved but still reflects the imprint of non-axisymmetric forces, with gas drifting along the arms while also slowly changing radius. Such non-circular motions are expected in barred disks and arise naturally when gas responds to a rotating perturbation in the gravitational field. Over many orbital periods, they help transfer angular momentum outward in the disk and allow some material to drift inward, even though at any given time most of the gas simply follows the imposed pattern. Within the molecular complexes themselves, narrower line widths in some clumps suggest relatively quiescent conditions, while broader profiles in others indicate higher levels of internal turbulence, perhaps stirred by recent star formation by shear or by the passage of shocks. The balance between quiescent and turbulent clouds sets how efficiently gas converts into stars in different parts of the inner disk. Regions along the bar that experience strong shear may host large amounts of molecular gas, but form stars only slowly, while slightly downstream in areas where shear is weaker, the same gas can fragment and collapse more readily. This spatial offset between gas peaks and star-forming knots is a common feature of barred galaxies and reflects the interplay between gravitational forcing and the timescales for cloud collapse. Perpendicular to the disk plane, the densest molecular and dusty material is confined to a relatively thin layer, while lower density gas and small dust grains extend farther above and below the midplane, forming a thicker, more diffuse component that gradually blends into the surrounding atomic halo. Within the thin layer shielded by dust and by the outer parts of clouds allows molecules to survive against dissociating ultraviolet radiation, so that carbon monoxide and molecular hydrogen remain abundant in the darkest interiors. Their temperatures fall to values of only a few tens of Kelvin, and the gas becomes susceptible to even modest pressures that can trigger further collapse. In this setting, the inner disk of the galaxy operates as both a repository for much of its cold gas, and as the main arena where dense dusty structures form, evolve and disperse under the combined influence of gravity, rotation, turbulence, and star formation. Over long time scales, enrichment by successive generations of stars gradually increases the proportion of heavier elements in this cold phase, changing the cooling behavior of the gas and the abundance of dust grains that help regulate temperature and shield molecules. As a result, the molecular and dusty component in the inner disk today carries a record of many cycles of gas inflow, cloud formation, star birth, and feedback imprinted in its composition structure and motions across the central few kiloparsecs. On galactic scales, the motions of stars and gas in the barred spiral disk form a complex but ordered pattern that reflects the underlying distribution of mass in the system. Observers measure these motions by taking spectra along many lines across the disk and along the bar using the slight shifts in wavelength of absorption and emission features to infer how fast material is moving toward or away from Earth. In the starlight, absorption lines broaden and shift because countless individual stars move with slightly different velocities along a given line of sight, while in the gas narrow emission lines trace the motion of distinct clouds and ionized regions. When these measurements are combined into two-dimensional maps, they show that the disk as a whole rotates in a well-defined sense, with material on one side of the major axis approaching and material on the opposite side receding. Far from the center, the rotation speed remains almost constant with radius, giving the nearly flat rotation curve seen in many spiral galaxies. This behavior indicates that most of the mass is not concentrated only where the stars are brightest, but is spread through an extended halo of dark matter that surrounds the visible disk. Closer in, within a few kiloparsecs of the center, the velocity field begins to deviate from the simple pattern expected for a thin, perfectly axis-symmetric disk. Along the bar, gas flows do not follow circular paths, but instead stream along the length of the bar, shifting gradually inward as they move. In the reference frame that rotates with the bar, pattern gas often encounters shocks where its orbits crowd together near the leading edges of the bar, and at these locations the observed velocities change sharply over short distances. In spectra, this appears as sudden jumps in the line centroids and as asymmetric profiles where different velocity components overlap. Stars, by contrast, respond to the bar potential more smoothly because their motions are dominated by the combined gravitational pull of the whole disk and halo rather than by pressure forces. Their orbits elongate along the bar, forming families of paths that support the bar shape for long times, and their velocity distribution becomes more anisotropic with larger dispersions along some directions than others. The difference between the stellar and gaseous responses is especially clear when one compares long slit cuts taken parallel and perpendicular to the bar. Along some directions, gas velocities climb steeply toward the centre, while along others they show wiggles and plateaus, as the flow bends around the bar and spiral arms. These non-circular components encode how effectively the bar transfers angular momentum from one part of the disk to another. In regions near resonances where the orbital frequency of stars and gas matches particular multiples of the bar's rotation rate, small perturbations can accumulate over many orbits and significantly change the shapes of paths. At certain radii, material may linger in ring-like zones, where orbits crowd together, while at others it may be driven either inward or outward depending on how the gravitational torques act. The inner disk of this galaxy likely hosts such resonances, although their exact locations depend on details of the mass distribution and on how quickly the bar itself rotates. Vertical motions add further structure to the kinematics. In the outer disk, stars follow slightly warped planes bending above and below the midplane as they orbit, a reminder that the disk is not perfectly rigid, but flexes under the influence of tidal forces from the companion and the broader group. Gas in the outer layers follows these warps but also feels pressure and may settle differently over time, sometimes forming a thicker flared layer in the outskirts than in the main stellar disk. Within the inner few kiloparsecs where the bar dominates, the vertical distribution of stars becomes somewhat thicker than in the outer disk, reflecting the fact that bar formation can heat stellar orbits and lift them into a more box-shaped or peanut-like bulge. This thickening changes the line-of-sight velocity profiles, increasing the spread in measured stellar speeds near the centre compared with the quieter outskirts. Superposed on the ordered rotation and bar-driven streaming are random motions associated with turbulence in the gas and with the velocity dispersion of stars. In star-forming regions, massive stars inject energy into the surrounding medium through stellar winds and supernova explosions, stirring up turbulence that broadens emission lines and creates small-scale irregularities in the velocity field. In older parts of the disk, repeated passages through spiral arms and the cumulative effect of gravitational encounters gradually increase the random speeds of stars, making their orbits less perfectly circular. The balance between ordered and random motion can be quantified by comparing the average rotation speed to the velocity dispersion. In the thin outer disk, rotation dominates and the ratio is high while closer to the centre, and in the bar the dispersion becomes more important and the ratio decreases. Where gas flows converge, shocks compress clouds and can lead to star formation, but the same shocks also create sharp gradients in velocity and density that may fragment the gas and produce complex filamentary structures. In the tidal, features that extend beyond the main disk velocities deviate further from the simple pattern of disk rotation. Some parts of the tidal tails share the general sense of rotation, but with offset speeds, while others loop back around in ways that indicate past close passages with the dwarf companion. The extended neutral hydrogen envelope carries imprints of these encounters in the form of kinematic twists and asymmetries that would not be present in an isolated, undisturbed disk. Together, stellar absorption line profiles, gas emission line velocities, and radio measurements of hydrogen form a layered view of how matter moves across the galaxy on kiloparsec scales. Over timescales of many hundreds of millions of years, these motions allow angular momentum to be exchanged between different components, gradually redistributing mass within the disk and halo, while the large-scale pattern of bar arms and warped outer layers persists. Moving inward from the bar and inner spiral arms, the disk transitions into a circumnuclear zone, where gas and stars crowd together within a region only a few hundred parsecs across. In this part of the galaxy, gravity bar-driven torques and orbital resonances combine to concentrate large amounts of cold molecular gas near the centre. Maps of emission from molecules such as carbon monoxide show that the surface density of this gas rises sharply toward the inner few hundred parsecs, reaching values far above those in the outer disk. Instead of forming a smooth central peak, the distribution often takes the form of an incomplete ring or a set of bright arcs encircling the nucleus at a characteristic radius. In some directions, the ring appears well defined, while in others it breaks into clumps and filaments, showing that the structure is not a perfect circle, but a dynamically evolving pattern, shaped by inflow along the bar and by local instabilities. Dust lanes that run along the bar on larger scales curve inward and connect to this ring-like feature, indicating that gas follows these lanes toward the centre and then piles up where orbital conditions slow its inward progress. The result is a dense, dusty circumnuclear region that marks a boundary between the larger scale disk dynamics and the inner nuclear environment. Within this zone, star formation becomes particularly intense. Observations in hydrogen recombination lines and in the ultraviolet reveal chains of young star clusters embedded in the dense gas arranged along the ring or along the brightest arcs. These clusters contain massive short-lived stars that produce strong ionizing radiation and powerful winds. Their light makes the circumnuclear gas glow in characteristic lines and heats nearby dust grains, which then emit strongly in the infrared. The presence of these young populations shows that the inward transport of gas does not lead directly to accretion onto the central object. Instead, a substantial fraction of the inflowing material forms new stars in the inner disk before any remainder can move deeper into the nucleus. The balance between gas consumed in star formation and gas that continues inward depends on conditions such as gas density pressure and the strength of feedback from the newly formed stars. Spectroscopic observations across this region show complex kinematics. Velocities along the line of sight reveal rotation around the centre as expected in a disk, but they also show non-circular motions and gradients that reflect streaming along the bar shocks at the points where gas meets the ring and possible inflow along spiral-like structures inside the ring. In some sectors, the gas appears to move slightly inward as it orbits tracing paths that curve toward the nucleus, rather than remaining on closed circular orbits. In others, the motion is closer to circular, suggesting that gas can be temporarily trapped near resonances where the gravitational influence of the bar and the overall disk pattern creates stable orbits. Line widths in the molecular emission vary across the region. Narrower lines in some clumps indicate relatively calm, cold gas capable of collapsing further, while broader lines in others point to higher turbulence, perhaps stirred by winds and supernova explosions, from recent star formation by shear in the velocity field, or by shocks where different streams intersect. This mixture of calm and agitated zones is characteristic of circumnuclear regions, where many processes act on overlapping spatial and temporal scales. The geometry of the gas and dust also affects how radiation from the central parts of the galaxy interacts with the surrounding material. Dense concentrations in the ring can shield regions on their far sides from direct exposure to strong radiation, creating pockets where molecules survive and cool efficiently. More diffuse gaps permit radiation to escape more easily into the broader disk and into the lower density halo above and below the plane. Infrared observations reveal that dust temperatures in the circumnuclear zone span a wide range from relatively cool grains in shielded molecular clumps to warmer grains near regions of intense star formation and closer to the nucleus. This spread in temperature reflects the intricate arrangement of gas dust and young stars within a small volume. Perpendicular to the disk, the circumnuclear gas remains relatively thin compared with its radial extent, but the vertical structure is still thicker than in the outer disk. Some gas and dust extend above and below the midplane in the form of a low-scale height atmosphere, possibly supported by turbulence and by energy input from young stars. This atmosphere may connect to larger scale outflows that emerge from the central regions, though the details of that connection require a closer look at the ionized gas and higher energy processes nearer the nucleus. For now, the main impression is that of a dense rotating and partially ring-like complex, where inflowing gas accumulates, forms stars, and slowly reconfigures the inner mass distribution of the galaxy. Over many tens or hundreds of millions of years, repeated episodes of inflow and star formation can build up a central concentration of stars in this region, adding to the bulge and altering the gravitational potential felt by gas that continues to move inward. In this way, the circumnuclear zone acts both as a sink drawing in gas from the larger disk and as a source injecting newly formed stars-enriched gas and energy into the inner environment that surrounds the very centre. Moving inward again from the circumnuclear ring, the inner few hundred parsecs of the galaxy reveal a far more irregular pattern of dust and gas, where well-defined lanes give way to tangled filaments, patches and knots that cross the bright central light in complex ways. High-resolution images show that the region around the optical nucleus is crossed by several narrow dark features that do not simply follow smooth arcs, but twist, fork, and intersect, creating a mottled appearance in which some parts of the underlying stellar background are heavily dimmed while others remain clear. These dusty structures span scales of a few tens of parsecs, with widths much smaller than their lengths, and many of them appear slightly curved or fragmented as though they have been stretched, compressed, and sheared by changing gravitational and pressure forces. Some filaments can be traced back toward the larger scale dust lanes along the bar or into the inner spiral arms, suggesting that gas and dust reaching the circumnuclear zone continue inward along preferred paths. Others seem to turn abruptly near the centre, or to terminate in compact clumps that sit close to the point of maximum nuclear brightness, indicating that local conditions can redirect or concentrate the inflowing material. The overall impression is not of a single coherent nuclear dust spiral, but of a patchwork of intersecting lanes and arcs, whose combined effect is to give the inner region a chaotic, asymmetric character. In many directions, the dusty features lie slightly off the midplane implied by the larger-scale disk-casting shadows that are strongest on one side of the nucleus and weaker on the other. This asymmetry means that the central source appears more obscured from some viewing angles than from others, even on scales of only a few tens of parsecs. In the optical, especially at shorter wavelengths, these lanes stand out with high contrast against the smooth glow of the central stellar component, while in the near-infrared they become more transparent but still trace the densest concentrations of cold material. By comparing images at different wavelengths, astronomers infer that the dust is mixed with significant amounts of gas, forming a multi-phase medium in which cold, dense clumps coexist with warmer, more diffuse components. In regions where the dust lanes are thickest, the column density of gas is high enough to shield molecules from dissociating radiation, allowing molecular gas to survive close to the centre. Elsewhere, thinner filaments and more ragged dust patches coincide with ionized gas visible in emission lines, where radiation from young stars in the circumnuclear zone or from the active nucleus has removed electrons from atoms and created glowing clouds embedded within the dusty network. Kinematic measurements in these inner regions show that gas following the dusty filaments does not simply rotate on circular orbits. Instead, velocities vary along the length of the structures, with components that curve toward or away from the nucleus, and with abrupt changes where filaments bend, fork, or intersect. In some locations, the motion appears to be inward along narrow channels, hinting that these lanes act as conduits, by which gas loses angular momentum and drifts closer to the centre. In others, velocity gradients suggest that material is being disturbed or lifted from the disk plane, perhaps forming the base of small-scale outflows, or fountains that rise a short distance before cooling and falling back. Superposed on these ordered components is a significant level of turbulence, evidenced by broadened line profiles and irregular small-scale shifts in velocity. This turbulence likely arises from a combination of gravitational instability shocks, where different flows collide, and energy input from star formation in the surrounding circumnuclear ring. As gas streams inward from larger radii, it encounters changing gravitational torques, spiral-like perturbations, and the influence of the central mass concentration. These factors break up smooth inflow into braided filamentary paths with dust marking the highest density portions of the flow. At the same time, radiation from the central region and from young stars in the inner few hundred parsecs heats and erodes the surfaces of dusty clouds, carving cavities and low-density channels between denser cores. The result is a three-dimensional arrangement in which some filaments hug the disk plane, while others arch above or below it, producing a layered pattern of absorption and emission when projected onto the sky. Color maps constructed from optical and near-infrared images show strong reddening along the filaments, confirming that they contain enough small grains to preferentially block blue light. In places where the extinction is patchy rather than continuous stars projected behind gaps between filaments appear in sharp contrast to neighbouring darkened regions, emphasizing how thin some of the structures are along the line of sight. On very small scales near the unresolved nucleus, the dust distribution becomes increasingly difficult to separate from the bright point-like light of the active centre, but subtle gradients and irregularities in the surrounding brightness still point to the presence of tiny clumps and wisps of absorbing material. Time-variable changes in the amount of obscuration along some lines of sight seen most clearly in X-ray, and ultraviolet observations indicate that individual dusty and gaseous clouds move across the central source on timescales of months to years. This behavior implies that at least part of the obscuring medium consists of compact structures orbiting at distances of fractions of a parsec to a few parsecs distinct from the larger scale filaments, tens to hundreds of parsecs across. Even so, the larger filaments and lanes that fill the inner few hundred parsecs shape how gas and dust from the circumnuclear zone approach the very center of the galaxy, because they regulate where dense material accumulates, where it is dispersed, and where the central light can emerge most directly through the uneven evolving screen of dusty structures. In the zone just outside the luminous center, gas lifted from the inner disk and circumnuclear ring forms an extended region of ionized clouds that surrounds the nucleus on scales of hundreds of parsecs. Astronomers refer to this domain as the narrow line region, because the emission lines produced by the gas are relatively narrow in wavelength, compared with those from gas that orbits very close to the central black hole. The clouds here move at moderate speeds of a few hundred kilometers per second, rather than the much higher velocities near the accretion flow, and their motions are influenced both by the gravity of the inner galaxy and by winds and radiation that stream out from the active nucleus. Images taken in strong emission lines show that the ionized gas is not spread evenly around the center. Instead, it often lies in elongated lobes or cone-like structures that extend on one or both sides of the nucleus. In this galaxy, the brightest part of this region appears offset from the disk plane and stretches outward along a rough axis that is misaligned with the large-scale bar and spiral arms. One side of the structure stands out more clearly, while the opposite side is more heavily dimmed by dust in the inner disk and circumnuclear filaments, so the ionized gas presents an asymmetric appearance in projection. Within the bright lobe, compact knots and filaments of emission line gas sit embedded in a softer background glow, marking pockets where density, temperature, and ionizing radiation combine to produce especially strong line emission. Spectra of these knots reveal a rich set of lines from atoms and ions at many stages of ionization. Ratios between certain lines show that the gas is mainly excited by the intense ultraviolet and X-ray radiation from the nucleus, rather than by shocks or by nearby young stars. The same spectra also provide estimates of gas density and temperature, which are typically lower and cooler than in the innermost broadline region, but higher than in the diffuse interstellar medium of the outer disk. Line profiles across the region indicate that gas is flowing outward from the centre. On the side of the galaxy that is tilted slightly toward Earth, many of the emission lines are blue-shifted relative to the systemic velocity, indicating motion along the line of sight toward the observer. On the far side, where dust and stellar light make measurements more difficult, red-shifted components mark gas moving away. Together, these features suggest a biconical outflow oriented so that one cone points partially toward Earth and the other away, with the disk and its dusty inner structures blocking parts of the far cone. The outflow does not consist only of ionized gas. Observations at infrared and millimeter wavelengths detect warm molecular gas and colder molecular components in roughly the same region. In some directions, emission from molecular hydrogen traces arcs and filaments that are slightly displaced from the brightest ionized features, but follow a similar overall geometry, indicating that different phases of gas share the same general flow while occupying different layers or clumps within it. The molecular gas moves more slowly on average than the hottest ionized component, with typical speeds of tens to a few hundred kilometers per second, and shows both rotational and radial motions. This suggests that some of the molecular material is being lifted from the inner disk and circumnuclear ring, rather than launched directly from the immediate vicinity of the accretion disk. Dust grains are mixed into these flows as well. Scattered light from the nucleus and from the inner star-forming regions illuminates the dust, creating faint reflection structures that outline parts of the cones. At the same time, the presence of dust affects how far ionizing radiation can penetrate into the surrounding gas, shaping the ionization structure of the outflow. Close to the axis of the cones, where the radiation field is strongest, and the column density of dust is relatively low, gas becomes highly ionized and produces strong lines from more highly charged species. Away from the axis in regions where dust and gas columns are thicker, ionization states are lower, and line ratios change accordingly. Perpendicular to the cones in directions closer to the plane of the disk, radiation encounters the dense dusty filaments described earlier and is absorbed or scattered before it can ionize large volumes of gas. As a result, the narrow line region is confined to certain angular sectors around the nucleus rather than forming a complete shell. Kinematic maps constructed from many spectra across this inner field show velocity gradients along the cones, with speeds generally highest near the nucleus, and declining with distance, though local variations are common where the flow interacts with clouds. In some places, shocks form where the outflow encounters denser clumps of gas from the circumnuclear region. These shocks can compress the gas and enhance certain emission lines, while also slowing or deflecting parts of the flow. Elsewhere, the outflow finds lower density channels and continues relatively unimpeded to larger radii. At heights of several hundred parsecs above and below the disk plane, ionized filaments and diffuse emission show that the influence of the outflow extends well into the lower halo of the galaxy. There the gas density falls and the radiation field softens, but the signature of motion away from the center remains detectable in broadened and shifted lines. Mass outflow rates inferred from the observed densities, velocities and volumes are sufficient to carry significant amounts of gas out of the innermost few hundred parsecs over timescales of tens of millions of years. Whether this gas escapes the galaxy entirely or eventually slows and falls back depends on the detailed mass distribution and on how the outflow evolves, but in any case the flow injects energy, momentum and chemically enriched material into the inner halo and outer disk. In this region, the outflow consists of ionized warm molecular and colder components, and each phase responds in its own way to radiation pressure, thermal pressure and gravity as it moves away from the nucleus through the irregular environment created by the inner disk and its dust-laden structures. Closer to the very centre of the galaxy, the bright nucleus that marks it as a Seyfert system becomes the dominant feature concentrated into a region so small that even large telescopes on Earth see it as a point of light. In physical terms, this nucleus is an active galactic nucleus, a compact zone where a massive black hole draws in gas and dust and converts gravitational energy into radiation over a wide range of wavelengths. Spectra of the central light show a smooth underlying continuum that rises from the optical into the ultraviolet and extends into X-rays different from the combined starlight of the surrounding bulge and disk. Superposed on this continuum are emission lines from gas at many ionization states. Some of these lines are narrow, similar to those seen in the extended ionized clouds farther out, while others are very broad with wings that span several thousands of kilometers per second in velocity. The broad features come from gas that orbits much closer to the central mass in what astronomers call the broad line region, a swarm of clouds or streams moving so rapidly that their individual motions blur together into wide spectral profiles. The narrow components arise in the more distant narrow line region, where gas moves more slowly and feels a weaker gravitational pull from the central object. The coexistence of both broad and narrow components in the spectrum of this nucleus confirms that the active centre is layered with distinct zones at different distances from the black hole. Estimates based on the width of the broad lines and on how quickly the central light varies suggest that the black hole has a mass of several tens of millions of times the mass of the Sun. Variations in the continuum brightness and in the strength of the broad lines occur on timescales of days to months. By measuring the delay between changes in the continuum and the corresponding response in the lines, a technique known as reverberation mapping, astronomers infer the characteristic size of the broad line region. In this system, that size is of the order of a light days to light weeks, meaning that the gas producing the broad lines orbits within a radius measured in only a few hundredths of a parsec. At these distances, gravity from the black hole dominates over the mass of the surrounding stars, so the motions of the gas mainly reflect the central potential. Within this radius, matter is thought to settle into an accretion disk, a rotating structure of hot gas that gradually spirals inward as it loses energy, although the fine details of this disk belong to even smaller radii closer to the black hole. Above and below the disk lies a region of very hot tenuous gas known as the corona, a kind of extremely energetic plasma that scatters photons to X-ray energies and produces the hard X-ray components seen in observations of the nucleus. The combination of the disk and corona provides the intense continuum radiation that illuminates the broad and narrow line regions, sets their ionization state, and exerts radiation pressure on nearby gas and dust. Surrounding the broad line region on somewhat larger scales is a distribution of cooler molecular gas and dust, arranged in a thick, roughly toroidal configuration. This dusty structure, often called the molecular torus, occupies radii of the order of a few parsecs. Its exact shape is not directly imaged, but its presence is inferred from several lines of evidence. Infrared observations reveal strong emission from warm dust grains that have been heated by the central radiation field, implying that a large mass of dusty material lies close enough to absorb and re-radiate this energy. At the same time, observations at X-ray and optical wavelengths show that the nucleus is sometimes heavily obscured along certain lines of sight, with absorption features indicating columns of gas and dust, dense enough to block or scatter much of the direct light from the inner regions. The torus provides a natural way to account for these phenomena. In directions that pass through its thicker parts, the central engine and broad line region are hidden, and their light reaches the observer only after scattering off more distant gas and dust. while in directions that look through its openings the nucleus is seen more directly. In this galaxy, the presence of both broad and narrow lines in the direct spectrum indicates that the view toward the centre is at least partially unobstructed, but signatures of absorption and variable obscuration show that clumps within the torus, or in closely related dusty structures, still intercept part of the line of sight. The torus does more than block light. Its mass and geometry influence how gas flows from the larger circumnuclear environment toward the immediate vicinity of the black hole. Gas arriving from the inner disk and ring encounters the outer edge of the torus and must lose additional angular momentum to pass through or around this thick rotating layer. Some material may become part of the torus itself, orbiting in a turbulent, clumpy medium that slowly evolves under the combined effects of gravity radiation and magnetic fields. Other material may be deflected away from the equatorial plane and guided toward the polar directions, where it can join the outflows traced by the ionized and molecular gas on larger scales. The inner edge of the dusty structure is set by the point where dust grains can survive the intense radiation from the center. Inside that radius, temperatures would be high enough to destroy most solid particles, so the medium becomes predominantly gaseous. Outside, dust remains stable and can efficiently absorb and re-radiate energy, making the torus a bright source in the infrared. These layers from the narrow line region at hundreds of parsecs through the dusty torus, at parsec scales down to the broad line region, at light day scales and the unresolved core of disk and corona closer in form, a nested system around the central black hole. Each layer has its own characteristic density temperature motion and dominant form of matter, yet all are coupled by gravity and radiation from the compact engine at the centre of the galaxy. The dusty and gaseous structures that surround the active nucleus do not form a smooth, uniform screen. Instead, they are clumpy and uneven, so that the amount of obscuration along any given line of sight can change with time as individual clouds move across the view of the central source. This variability becomes most apparent in X-ray observations, where the high-energy continuum from the innermost regions passes through the circumnuclear medium and is absorbed in a way that depends sensitively on the number of atoms and dust grains in its path. At some epochs, the X-ray spectrum of the nucleus shows strong absorption at low energies, indicating that the line of sight intersects dense gas-rich clouds that block a large fraction of the soft photons. At other times, the absorption is weaker and the continuum appears relatively unobscured. These changes can occur on timescales ranging from days to months, far shorter than the orbital periods at kiloparsec scales. Such rapid variations imply that at least part of the obscuring material lies at distances of the order of only a few light days to a few light months from the central engine in compact clumps that cross the line of sight as they follow their orbits in the gravitational potential of the inner regions. By measuring how quickly the absorption strengthens and weakens, astronomers estimate the sizes of these clumps. A cloud that covers and then uncovers the compact X-ray emitting region over a period of weeks must have a characteristic dimension comparable to the projected size of the emitting region multiplied by the transverse velocity of the cloud. Using typical orbital speeds for material at parsec and subparsec radii around a black hole of several tens of millions of solar masses, these estimates yield cloud sizes of fractions of a light year and densities high enough to qualify as parts of the same dense, dusty medium that forms the molecular torus and related circumnuclear structures. In some events, the increase in column density is so strong that the nucleus appears almost completely hidden in soft X-rays, for a time a phenomenon often described as an eclipse by a passing cloud. When the cloud moves on, the spectrum returns to a less absorbed state. Such occultations provide direct evidence that the torus and associated dusty gas are not continuous, but are built from many individual entities whose orbits and internal densities vary within a broad range. In the optical and ultraviolet, similar although less dramatic changes appear as shifts in reddening and in the detailed shape of the continuum. At times, the nuclear light looks somewhat redder or more strongly curved at short wavelengths, signalling that an extra layer of dust has moved into the line of sight and is absorbing and scattering more of the blue and ultraviolet photons than usual. At other times, the spectrum is bluer and closer to the intrinsic shape expected from the accretion flow and its immediate surroundings, suggesting a clearer view. In some monitoring campaigns, variations in line strengths accompany these continuum changes. The broad emission lines sometimes respond in ways that are not purely tied to the intrinsic luminosity of the central engine, but also to how much of the line-emitting region is screened or shadowed by intervening dust. This complex behavior underscores that the broad line clouds and the dusty obscuras occupy overlapping but distinct volumes in the inner few parsecs. Polarization measurements add another dimension to the picture. Light that reaches Earth after scattering off free electrons or dust grains in regions above and below the main obscuring plane becomes polarized, and the orientation and degree of that polarization depend on the geometry of the scattering regions and the locations of the obscuring clumps. In this galaxy, the presence of polarized broad emission lines in some observations indicates that, even when the direct view of part of the broad line region is blocked, scattered light can still carry information about it along less obscured paths. The combination of direct and scattered components, each modulated by time, varying obscuration, produces a nuclear spectrum whose detailed shape and polarization properties shift over periods much shorter than the structural timescales of the overall torus. On somewhat larger scales, tens of parsecs from the center, the dusty filaments and patches described earlier also contribute to an uneven pattern of attenuation across the inner field. As they orbit and respond to gravitational torques from the bar bulge and central mass, these filaments can alter which parts of the inner, more compact obscuring structure are visible from Earth. A cloud moving through the line of nodes of the disk may for a time reinforce the obscuration from the torus along a particular direction, deepening the shadows in optical images and adding to the effective column seen in X-rays, while in other directions the same motion might open a clearer channel. Thus, the total obscuration toward the active nucleus at any given moment reflects the combined effect of material on several spatial scales. Compact clumps in or near the torus at parsec and subparsec radii, somewhat more extended clumps in the inner few tens of parsecs and larger filaments in the circumnuclear zone. The distribution of dust and gas in these regions is shaped by a variety of processes. Inflows from the circumnuclear ring feed fresh material into the inner structure, adding new clouds and filaments whose orbits and internal properties depend on how they entered and how they interact with the existing medium. Radiation pressure from the central engine acts preferentially on dust grains pushing on them and on the gas that is coupled to them by collisions and electromagnetic forces. In directions where radiation is strongest and where the column densities are moderate, this pressure can accelerate clumps outward, thinning the obscuring layer or even launching part of it into the polar outflows. In regions where the column is higher and gravity dominates, dust can survive and remain bound, forming thick, slowly evolving structures that continue to intercept light. Turbulence, magnetic fields, and thermal instabilities further fragment the gas and dust into a spectrum of densities and sizes, promoting the growth of dense cores inside more diffuse envelopes. Over time, some clouds may partially evaporate under the influence of the intense radiation and hot surrounding plasma, while others grow by accreting material from their surroundings. The net result is a constantly changing clumpy medium that shifts the balance between transparent and opaque sightlines, according to the detailed time-dependent arrangement of its constituents. Even though the broad architecture of disk corona broadline region and torus remains relatively stable over many dynamical times, the fine structure of the circumnuclear dust and gas, and hence the pattern of obscuration, continues to evolve on much shorter timescales that can be traced in multi-wavelength monitoring of the active nucleus. Inside the clumpy dusty structures on parsec scales, gas and dust continue their slow journey toward the central black hole, passing from the realm where large-scale bars and circumnuclear rings dominate into a zone where local processes in a compact rotating flow take over. In this intermediate region, distances from the center shrink from a few parsecs to fractions of a parsec, and orbital speeds rise until the motion of the gas is set mainly by the gravity of the central mass rather than by the surrounding stars. Clouds and streams that have reached the inner edge of the molecular torus orbit on paths that are close to Keplerian, meaning that their motion is largely determined by the simple pull of a central object, but they still carry substantial angular momentum and cannot fall straight inward. To continue moving closer, they must lose part of that angular momentum, and this loss occurs through a combination of collisions between clumps, turbulent motions within clouds, and stresses exerted by magnetic fields that thread the gas. Within the torus, individual clouds follow intersecting orbits in a thick rotating layer. When two such clouds pass near each other, their mutual gravity and the pressure of the gas can cause them to merge, fragment, or exchange energy. In some encounters, part of the combined material is left on a slightly tighter orbit, while another part moves outward. This process redistributes angular momentum among the clouds and helps a fraction of the gas slip inward step by step. At the same time, shear in the rotating flow stretches clouds along the direction of motion and compresses them in the perpendicular directions. The stretching increases the surface area of the clouds and brings them into closer contact with the surrounding diffuse medium, promoting mixing through turbulent eddies and through thermal conduction between hotter and cooler phases. Some clouds partially evaporate into the surrounding gas, seeding it with denser patches that can later cool and condense again at slightly smaller radii. Magnetic fields add another channel through which angular momentum can be transported. The rotating gas drags the field lines into spiral shapes, and small disturbances in this magnetized flow can grow into patterns where regions of gas at slightly different radii exchange angular momentum by pulling on the shared field. Gas that loses angular momentum in this way drifts inward while gas that gains it moves outward. This magnetically driven turbulence does not require large collisions between whole clouds. It can operate continuously in the diffuse component and in the outer layers of clumps, creating a background of irregular motion that both stirs the gas and supports a net inward drift of mass. Radiative forces also influence the flows. Close to the inner edge of the dusty torus, dust grains are heated by the intense radiation from the accretion flow and corona inside. Grains that move slightly inward can reach temperatures where they begin to sublimate, turning from solid to gas. When this happens, the local opacity of the medium changes, and the gas that was previously supported in part by radiation pressure on dust now responds differently to the central light. In directions where radiation pressure is strong and the column densities are moderate, some gas is accelerated outward into winds that feed the larger scale outflows seen in the narrow line region. In directions closer to the equatorial plane, where gravity and pressure confinement from surrounding material are stronger, gas can remain bound and continue its inward motion. The boundary between these regimes is not sharp, but depends on local density composition and illumination, so the inflow and outflow coexist in a layered pattern around the nucleus. Observations of absorption, features in ultraviolet and X-ray spectra, reveal components of gas that move inward toward the center, as well as components that move outward. Some absorption lines show small redshifts relative to the systemic velocity of the galaxy, indicating gas that is drifting inward along the line of sight at speeds of tens to a few hundreds of kilometers per second. These inflowing components are often moderately ionized, forming what is sometimes called warm gas, and they may represent material that has recently passed the dust sublimation radius and is still adjusting to the conditions in the inner flow. Other absorption lines are blue-shifted and trace outflowing gas, showing that the net motion in this region is not a simple one-way stream, but a superposition of many trajectories. The inflowing part of this pattern carries mass toward the radii, where an accretion disk forms, while the outflowing part removes mass and angular momentum from the vicinity of the disk and helps shape the surrounding environment. Because the inflow is clumpy and intermittent, the supply of gas to smaller radii is not perfectly steady. Over timescales of years to decades, changes in the distribution and density of clouds at the inner edge of the torus can alter how much material reaches the inner flow. These changes likely contribute to the observed variability of the active nucleus, adding slow modulations in the mass accretion rate to the faster variations that arise closer to the black hole. In some intervals, many clouds or dense streams may reach the inner region and feed a relatively high rate of inflow, brightening the nucleus. In other intervals, the available channels may be partially blocked or depleted, and the accretion rate may decline. Even when the average feeding rate from the larger galaxy is roughly constant over millions of years, this small-scale structure introduces fluctuations at shorter times. Geometrically, the inflowing gas near the inner edge of the torus begins to flatten as it moves deeper into the gravitational potential. Collisions between streams and the action of turbulence dissipate motions that are not aligned with the orbital plane, so the gas gradually settles into a thinner, more disk-like configuration. Closer in, where dust has largely vanished and the gas becomes hotter and more ionized, this configuration transitions into the classic accretion disk, in which material orbits in nearly circular paths while slowly spiraling inward. The zone described here is the region where that transition occurs, with parcels of gas passing from thick, clumpy, dusty orbits into a smoother, hotter, more organized flow. The temperature, density, and ionization state of the gas change rapidly over these scales, but the underlying requirement that angular momentum be removed in order for material to move inward continues to govern the overall behavior. Over long periods, the competition between inflow, driven by gravitational and magnetic processes, and outflow, driven by radiation pressure and thermal forces, sets the average rate at which mass can cross this interface and feed the deeper layers of the active nucleus. Closer in than the dusty, clumpy flows that mark the inner edge of the torus, the inflowing gas organizes into a flatter, hotter structure that is recognizable as an accretion disk. In this region, the distances from the central black hole are small enough that the gravitational field dominates over all other sources of force, and orbital speeds reach thousands of kilometers per second. Gas follows nearly circular paths in a thin, rotating layer, while friction-like processes within the disk slowly remove angular momentum and allow matter to spiral inward. These processes are not friction in the everyday sense, but arise from turbulence, magnetic stresses, and the continual shearing of neighboring gas layers that orbit at slightly different speeds. Together they transport angular momentum outward through the disk, while carrying energy inward, so that gravitational potential energy released by the infalling material is converted into heat and radiation. The structure of the disk depends on radius. Farther out where densities remain high and temperatures are lower, the gas can stay partially ionized and relatively opaque, cooling efficiently by emitting light in optical and ultraviolet bands. Closer in, the temperature rises as the material sinks deeper into the gravitational well, and the disk emits more strongly at ultraviolet and soft X-ray energies. In simple models, each ring of the disk radiates roughly like a warm surface, whose temperature increases steadily inward, but real disks include additional complications such as vertical temperature gradients, magnetic fields, and the influence of radiation produced in other parts of the nucleus. Even so, the idea of a radially stratified disk with cooler outer regions and hotter inner zones provides a useful framework for interpreting the emission from the active centre of the galaxy. Observationally, the presence of such a disk is inferred from the shape of the continuum spectrum. The rise from optical wavelengths into the ultraviolet and soft X-ray bands resembles the combined light of many nuclei at different temperatures, each contributing a portion of the overall output. Short-term variations in brightness also support this picture. When the central source brightens or dims, the changes at different wavelengths occur, with small but measurable time delays between them. These delays are consistent with light emitted in the innermost regions being reprocessed by gas and dust at slightly larger radii, indicating that a compact, rapidly varying source illuminates and heats the surrounding disk and circumnuclear material. Above and below the disk lies a more tenuous but extremely hot component known as the corona. This region consists of plasma so energetic that electrons reach temperatures of hundreds of billions of degrees, expressed in energy units, and are able to scatter lower energy photons to much higher energies through inverse Compton interactions. Soft photons from the disk enter the corona and collide with these hot electrons, gaining energy and emerging as X-rays. The resulting emission forms a hard X-ray continuum that is a characteristic feature of many active galactic nuclei, including this one. The geometry of the corona is not directly imaged, but various lines of evidence suggest that it is compact, compared with the disk perhaps concentrated within a few tens of gravitational radii of the black hole, and may take the form of a patchy layer above the disk, a collection of magnetic loop structures, or a more spherical region near the rotation axis. In any case, the corona sits close enough to the inner disk that their interactions shape much of the observed high-energy output. X-rays from the corona irradiate the surface of the disk, especially the inner rings. When these X-rays strike the disk, part of their energy is absorbed and reprocessed into lower energy light, while part is reflected or scattered back towards space. The reflected component carries distinctive spectral signatures, including fluorescent emission lines from elements such as iron, and a broad hump like excess at certain X-ray energies, where reflection is efficient. In some cases, relativistic effects near the black hole smear and skew the reflected lines into asymmetric shapes, leaving broad features that carry information about the strong gravity close to the center. The balance between direct coronal emission and reflected light from the disk provides clues about the height, size, and luminosity of the corona relative to the disk. Timing studies offer further insight. Rapid fluctuations in the X-ray brightness occurring on timescales of hours to days point to an emitting region no larger than a few light hours to light days across, because larger regions cannot vary coherently so quickly. Correlations between the X-ray variations and changes at longer wavelengths reveal how disturbances propagate through the system. In some monitoring campaigns, X-ray flares precede ultraviolet and optical brightenings by short delays consistent with a scenario in which the corona brightens first and then heats the disk, which responds with enhanced lower energy emission. In others, slower trends in the ultraviolet and optical bands reflect changes in the underlying accretion rate through the disk, which in turn modulate the power available to the corona. Thus, the disk and corona form a coupled system, exchanging energy and responding together to changes in the flow of matter toward the black hole. The efficiency with which the disk converts gravitational energy into radiation depends on the inner boundary where stable orbits give way to plunging infall. For a spinning black hole, that boundary lies closer to the event horizon than it does for a non-rotating one, and therefore the maximum possible efficiency can vary. Estimates based on the luminosity of the nucleus relative to the inferred accretion rate suggest that the system operates at a modest fraction of this theoretical maximum, so the disk shines brightly, but not at the extreme levels seen in the most luminous quasars. In such a regime, radiation pressure is important, but does not completely disrupt the inflow, allowing a relatively steady disk and corona to persist over long periods. At the same time, local instabilities within the disk, in which small changes in temperature or density grow and alter the balance between heating and cooling, can produce intrinsic variability on intermediate timescales. These instabilities arise naturally in models where viscosity, magnetic turbulence, and radiative cooling interact in a nonlinear way, and they offer one explanation for the flickering and multi-timescale variations observed in the continuum light. Through all of this, the accretion disk remains the main channel through which mass, angular momentum and energy move from the surrounding galaxy into the domain where the black hole's gravity is strongest, while the corona acts as a high-energy halo that amplifies and redistributes a portion of the disk's radiative output into the X-ray band. In the inner part of the accretion flow, where the thin disk and compact corona sit only a small number of gravitational radii from the central black hole, the exchange of energy and momentum between radiation magnetic fields and gas becomes intense enough to stir the surrounding medium into a highly turbulent state. In this region, gravity tries to draw matter steadily inward, but at the same time the disk and corona produce strong radiation high-energy particles and magnetized outflows that push back on the inflowing gas in multiple ways. The result is not a simple smooth flow, but a continuously changing pattern of clumps, filaments and waves in which some material continues to spiral inward, while other material is heated, lifted or expelled. Within the disk, magnetically driven turbulence transports angular momentum outward and allows mass to move inward, but it also creates fluctuations in density and temperature from place to place and from moment to moment. These fluctuations change the local rate at which gas cools and heats, which in turn alters how quickly it can sink deeper into the potential well. In some patches of the disk surface, the energy released by accretion and by irradiation from the corona heats the gas until its pressure becomes high enough to puff it up above the average disk thickness. In other patches, rapid cooling allows the gas to remain thinner and denser. The contrast between these zones seeds vertical motions that feed turbulence and help launch material away from the midplane. Near the inner rings of the disk, where orbital periods are very short, such variations can grow and decay on timescales of hours to days, so the flow is constantly reorganizing itself while maintaining an overall pattern of inward mass transport. Radiation from the disk and corona exerts pressure on the gas, especially on regions that are at least partially ionized, and on dust rains that may survive in slightly cooler zones just outside the hottest inner radii. In directions above and below the disk where gravity pulls less strongly than in the equatorial plane, and where the density can be lower, this radiation pressure can accelerate gas away from the disk surface and form winds. These winds can begin as thermally driven flows, where gas heated to high temperatures expands and escapes, or as line-driven flows where radiation interacts efficiently with certain atomic transitions and pushes on the gas through absorption and scattering. Once set in motion, the winds can carry mass momentum and energy into the surrounding regions, adding to the larger scale outflows seen hundreds of parsecs away, and modifying the conditions in the inner narrow line region. Closer to the equatorial plane, where densities remain higher and gravity holds gas more tightly, radiation pressure still contributes to the overall balance of forces, but is less able to launch material directly. Instead, it changes the vertical structure of the disk, thickening it into a somewhat puffed-up inner region, where gas motions include not only rotation and slow radial drift, but also vertical oscillations and turbulent eddies. Magnetic fields that thread the disk take on spiral and loop-like shapes as the plasma orbits. Instabilities in these fields can lead to the growth of twisted structures that rise above the disk's surface, reconnect and release energy in the corona. Each reconnection event accelerates particles and heats the local plasma, feeding the high-energy tail of the X-ray spectrum. At the same time, the changing magnetic stresses couple the corona to the disk below, shaking the upper layers of the disk and altering the pattern of turbulence. In some models, the corona may also drive magnetocentrifugal winds, in which gas attached to field lines inclined away from the disk is flung outward as it follows the rotating field, extracting angular momentum from the inner flow and contributing to the total outflow rate. Turbulence near the inner disk is not limited to small scales. Larger scale waves such as spiral density patterns and vertical bending modes can propagate through the flow, redistributing angular momentum and modulating the local density. When these waves reach the disk surface, they can channel energy into the upper layers and promote the formation of inhomogeneities. In effect, the inner flow consists of a superposition of many modes of motion: ordered rotation around the black hole, slow radial drift, inward vertical expansion and contraction, and irregular motions driven by turbulence and waves. These combined motions shape the distribution of gas that can interact with the central radiation and with any emerging winds. As gas is lifted from the disk surface by radiation and magnetic forces, it encounters zones of different density and pressure. In denser regions, it may slow, compress, and form clumps that remain bound relatively close to the disk, orbiting in a thick, turbulent atmosphere. In less dense regions, the gas can accelerate more freely and join the wider scale outflow that travels out to tens or hundreds of parsecs. The interface between the bound atmosphere and the escaping wind is not sharp, but diffuse, with material continually shifting from one behavior to the other. Some of the gas that initially rises may lose pressure support and fall back onto the disk, creating a fountain-like circulation in which matter cycles between the disk and its immediate surroundings before either accreting inward or escaping outward. This circulation, combined with the inflow from larger radii and the outflow toward larger scales, maintains a stirred, constantly replenished environment in the inner few tens of gravitational radii. The same processes that launch winds and heat the corona also act on the small-scale clumps in the circumnuclear region just outside the torus. High-energy photons and particles from the inner flow penetrate into nearby gas, heating its outer layers and driving evaporation flows off the surfaces of dense clumps. These flows add mass to the hot diffuse component and can erode the clumps over time, while at the same time the clumps respond by adjusting their internal pressure and density. Some clumps become more compact and resistant to further erosion, while others disperse. In this way, feedback from the innermost engine helps determine the size spectrum and survival times of clouds in the environment immediately surrounding the accretion disk. On yet smaller scales, close to the radius where stable circular orbits end the balance between gravitational attraction and all these feedback processes changes again. But even before that boundary, the combined effect of radiation, magnetic fields and turbulence has transformed the inflowing gas from a relatively cool, dusty, clumpy medium into a hot, ionized and highly structured flow that both feeds the black hole and stirs heats, and partially expels the material in its immediate vicinity. Very close to the central black hole at distances of only a few tens of gravitational radii, the flow of gas changes character again as it approaches the point beyond which nothing, not even light, can escape. In this innermost region, the curvature of space-time predicted by general relativity is strong, so that familiar ideas of straight paths and simple orbital motion no longer apply in the same way as they do in the outer disk. The thin rotating flow described on larger scales extends inward until it reaches the innermost stable circular orbit, a radius inside which gas can no longer remain on a steady circular path. The exact location of this boundary depends on how rapidly the black hole spins and on whether the gas orbits in the same direction or in the opposite direction to that spin, but in all realistic cases it lies only a small number of gravitational radii from the centre. Outside this orbit, gas orbits many times while slowly spiralling inward under the influence of magnetic turbulence and other stresses. Once it crosses this threshold, its path becomes a rapid inward plunge. Orbital energy and angular momentum are then transferred mainly through gravity, rather than through the slower processes that operate in the disk, and the time between crossing the innermost stable orbit and reaching the event horizon is short compared with the time spent in the outer parts of the disk. During the final orbits just outside this boundary, the gas reaches its highest orbital speeds and temperatures. Velocities there approach significant fractions of the speed of light, and the material becomes so hot and ionized that atoms are stripped of most of their electrons. Radiation produced in this region emerges at X-ray, and in some models even higher energies. However, not all of this radiation escapes to infinity. Because space-time is strongly curved, light rays do not travel in straight lines, but follow bent paths that can loop around the black hole or fall inward instead of propagating outward. Photons emitted from the innermost rings in directions that point even slightly toward the black hole may spiral inward and cross the event horizon, while those emitted outward along certain angles can climb out of the gravitational well and reach distant observers. The ones that do escape carry the imprint of the environment in which they were produced. Their energies are shifted by gravitational redshift, which lowers the energy of light climbing out of the deep potential, and by Doppler effects from the rapid orbital motion of the gas. As a result, emission lines from the inner disk appear broadened and skewed when seen in X-ray spectra with extended wings that trace the combination of fast rotation, strong gravity and light bending near the black hole. By modelling these line shapes, astronomers infer properties of the innermost flow, such as the inclination of the disk and constraints on the spin of the central object, although uncertainties remain, and different models can sometimes fit the data in similar ways. Within a few gravitational radii of the event horizon, magnetic fields anchored in the disk and in the plunging gas become especially important. Differential rotation wins these fields into tight spirals and can amplify their strength until magnetic pressure and tension rival the thermal and ram pressures of the plasma. In some configurations, field lines thread the region just outside the event horizon and connect to more distant parts of the flow or to the lower density medium along the rotation axis. These connections allow energy and angular momentum to be extracted from the rotating gas, and if the black hole itself carries spin possibly from the rotation of the hole. Part of this extracted energy can contribute to launching collimated outflows along the poles. In powerful quasars and radio galaxies, such processes are thought to produce large relativistic jets that extend far beyond their host galaxies. In a system like this, safe at nucleus, any jets or collimated flows are more modest in scale and luminosity, but similar physical principles may operate on smaller scales, helping to drive the inner portions of the outflows seen on circumnuclear and galactic scales. Near the innermost stable orbit, the disk surface is not completely smooth. Turbulent eddies, magnetic reconnection events, and small-scale density inhomogeneities create bright and faint patches that move rapidly around the black hole. As these patches orbit, their emission is modulated by relativistic beaming gravitational redshift and light travel time delays, producing subtle patterns in the observed X-ray variability. Some models describe this behavior in terms of hotspots or flares co-rotating with the disk, although the true pattern is likely a complex superposition of many transient features. Over time, these inhomogeneities are stretched, mixed, and advected inward, with the bulk flow so that the inner disk continually regenerates new structures, while older ones disappear into the black hole. The event horizon itself has no surface in the usual sense. It is a region from which light cannot emerge rather than a solid boundary. When gas crosses this horizon, its remaining radiation is cut off from the outside universe, and its detailed state can no longer be observed. The infalling matter still contributes mass energy and angular momentum to the black hole, changing the parameters that describe it on large scales. General relativity predicts that apart from these global quantities, little information about the original configuration of the gas survives in a form that affects the gravitational field outside. From the point of view of distant observers, the complicated structure of magnetic fields, turbulence and thermodynamic states in the innermost flow leaves its imprint mainly in the radiation emitted before crossing the horizon and in the gradual evolution of the black hole's mass and spin. The transition from the radiating inner disk to the dark interior marks a boundary in observational terms as well as in space-time structure. In the region just outside that boundary, matter experiences its final rearrangement under extreme gravity and magnetic forces, releasing the last fraction of its accessible energy before disappearing from view inside the event horizon.